Solving nonlinear equations with spreadsheets is an episode of the Degrees of Freedom project, videos on chemical and thermal principles. Definitions and additional details can be found at the webpage link in the description. This video, Solving Nonlinear Equations with Spreadsheets, doesn't have a clever title, but it is a discussion of 3 common techniques to find a root of nonlinear equations with a spreadsheet along with a demonstration. Most of the equations we've encountered to date in doing material balances have been in linear systems of equations. LibreOffice does have matrix functions and can solve systems of linear equations, but it's rarely worth the time to set things up. However, there are a number of equations that pop up in chemical and process engineering that are definitely nonlinear. First is the Antoine equation, which relates the vapor pressure of a substance to the temperature. The version in the NIST chemistry webbook relates pressure in bar to temperature in Kelvin. As written, you can solve for either P star as a function of T or T as a function of P star. However, once we get to Raoult's law, you'll find that we combine 2 Antoine equations into one equation, and you can no longer find an analytical solution. We've also seen the Arrhenius equation a few times. Again, you can solve for K as a function of T or T as a function of K in its present form. However, if you have 2 competing chemical reactions, you can end up with equations that can't be solved analytically for T. Finally, in our list today, we have the Benedict-Webb-Rubin equation. It is a replacement for the ideal gas law for real gases, and it can also predict PVT relationships for liquids as well. It has 8 fitting parameters, but finds frequent use in calculations involving light-end hydrocarbons. If you are given T and V and need to calculate P, it's easy to use. It's not too horrible if you're given P and V and need to calculate T, but if you're given P and T and need to calculate V, it's really horrible to use. So how do you find the roots of equations like these on a spreadsheet? Assuming you can't find an analytical solution, the first step is to set up the spreadsheet so that there is a particular cell for entering the value of the independent variable, x. Then set up another cell that has the formula for f of x, where the value is 0 if you are at a root. You then have your choice of methods. One that always works but can be tedious is to guess and check. Enter a value for x and check the value for f of x. Then enter another value for x and see. Did the value of f of x get smaller? If so, keep going in the same direction. If not, go the other way. Did f of x change sign? If so, then the root is between the last 2 values. Keep trying to bracket the root with your guesses. A step up from guess and check is to graph f of x and see where it crosses 0. Then keep making the graph interval smaller and smaller around the root. Finally, there is goal seek. For goal seek, you enter the reference for the cell containing f of x, then the value you want f of x to reach. I recommend 0. And finally, the cell containing x. You then hit OK. It does a sophisticated guess and check and stops when it's satisfied with x or can't find an answer. With nonlinear functions, you have to start close enough to a root that goal seek can work. Too far away, and you'll either get the wrong root or go off to infinity. Let's set up the previous equations as functions that equal 0. For the Antoine equation, you can either specify P star and find the value of T, or specify T and find the value of P star. Obviously, you can solve for either one analytically, but we're just doing it for demonstration purposes. Putting both sides of the equation on the same side of the equal sign, we get that the f of P star, or f of t, that should be 0 is equal to log 10 of P star minus a plus b over t plus c. Likewise, if we take the Arrhenius equation and convert it to f of t equals 0, the result is f of t equals k minus k naught exponential of negative ea over rt. For the Benedict-Webb-Rubin equation, we end up with f of v hat equals this rather long equation that I'm not about to read off. Now that we have the functions that equal 0 at the roots, what do? I'll do a few little demos with all 3 models on the Antoine equation, and then using goal seek on the BWR equation. Before we begin, you'll notice that the screen capture of the Antoine demonstration has the Antoine constants from the NIST chemistry webbook for acetone. These values are good from 259.16K to 507.6K. Directly below these, we have some analytical expressions for P star and T. Notice that the T's are in degrees C, even though the Antoine constants are in terms of K. That means that we had to add 273.15 to the temperature in the formulas to convert them to K. Below that, we have a goal seek area with T and P star. We'll first use it for guess and check. You could vary either T or P star, but we'll set T and guess P star. After the guess and check, we'll narrow in on a P star by graphing and making smaller and smaller P star ranges. Finally, we'll use goal seek on the goal seek regions. Then we'll click the next sheet and do the BWR equation for both the vapor phase root and the liquid phase root. We'll start with a little guess and check. We'll do it in the goal seek area. First, we'll guess 0.4 for P star. We notice that the sign changes, so it's between 0.4 and 0.5. We'll next guess 0.45. sign doesn't change, but the error gets smaller. Next, we'll try 0.47. The sign changed, so we know it's between 0.45 and 0.47. We'll try 0.46. The sign changed again, and the error is getting smaller. At this point, I'm going to stop and try the graphical method. By looking at the graph, we see that the function crosses 0 between 0.4 and 0.5. We'll do the enter two values and drag trick with 0.40 and 0.41. We see it crosses between 0.46 and 0.47. We'll use 0.460 and 0.461. It now crosses between 0.462 and 0.463. We'll enter 0.462 and 0.4621 and drag. It's awfully close to 0.4622. Next, we'll do goal seek. We'll select the set to 0 cell and start at our p star equals 0.46, which we know is close. Under the Tools menu, we'll choose Goal Seek. We may have to click on the Set to 0 cell if it doesn't come up pre-chosen. Click on Target Value and type in 0. Then click on Variable Cell and click on the P-star value. Then click OK. With any luck, you'll get the Goal Seek Succeeded window. Click on Yes. The result is roughly 0.462224. It's faster than the graphical method and has a lot faster than Guess Check. Now we'll click on the BWR tab. We're interested in the two regions labeled BWR Vapor and BWR Liquid. The BWR has three roots, one stable, one for vapor, one stable one for liquid, and one unstable one in between. We're looking at propane, and all of the BWR constants for propane are at the top of the page. The equation has been broken up into multiple terms because it's really hard to enter the whole thing without errors at one time. Basically, we've had the system pressure and temperature, then we calculate the ideal gas molar volume to give us a starting guess for the vapor molar volume. We'll do our step of clicking on the Set to 0 cell and then choosing Goal Seek from the Tools menu. Again, we have to click on the Set to 0 cell, then make sure the target's value is 0. Then we click on Variable Cell and choose the value to vary. We hit OK and fortunately get the Goal Seek Succeeded window. Click on Yes. The VVape is 0.5388 liters per mole. Now we'll try for the liquid molar volume. Our initial guess is much smaller than for the vapor because we want to hit the smaller root. The same sequence, choose Goal Seek from the Tools menu. Click on the Set to 0 cell, make sure the target value is 0, click in the Variable Cell box, and hit OK. With luck, we get the Goal Seek Succeeded dialog box. Click Yes. The liquid molar volume is 0.1085 liters per mole. It's fun to experiment with how far the guess can be from the correct value and still hit the correct root. It's also worthwhile to see how the spreadsheet is constructed and see how the formulas are implemented. Let's finish with a few suggestions for using Goal Seek. You can often force Goal Seek to find the root to more significant figures by multiplying f of x by a large number. The reason it works is that the algorithm in Goal Seek decides to terminate by how close f of x is to 0. If you multiply f of x by a large number, you have to have more sig figs in the value of x for f of x to be close enough to 0. I usually use 10 to the 8th, but feel free to experiment. I did this in both the Antoine equation demo and the BWR demo. I usually clearly mark both the f of x cell and the x cell, so that when I get to the Goal Seek dialog box, I can clearly see where I should click. Here's the f of x cell. The label is set to 0. Now, for setting the x value, here is the x cell. The label is value to vary. That should provide you with a good introduction to Goal Seek. A couple of final notes. Goal Seek works fine on linear functions. It is limited to functions of one variable. If you need to find the roots of a multivariable function like f of x and y equals 0, you can use solver. If you need to find the roots of two simultaneous nonlinear functions, you can iterate by using Goal Seek on one variable and then on the other and go back and forth until you find both roots. But at that point, you're probably better off using Python or R or some other programming language. The takeaways from this video are 1. You can find the roots of a nonlinear equation on a spreadsheet with Guess and Check, graphically, or with Goal Seek. If you're close enough to a root, Goal Seek is fastest, easiest, and most accurate. 2. Rewrite your function as f of x equals 0. 3. Multiply your f of x cell by 10 to the 8th to increase the sig figs in your x value. 4. Label your x and f of x cells so you can find them quickly. Thanks for watching. This video was brought to you by the DOFPro team.